Anyways, so now some hints about how to analyze and use the systems on or control systems on Octave, the very fundamentals. Actually, if you take a look at this control toolbox of Octave, you can see that actually it's quite comprehensive and it includes also some identification tools. So if you have measured data, then there are identification tools to find the say estimate for the system transfer function, which is usually the problem. If we have a real system, then it's quite easily gets so complex that it's hard to have a perfect mathematical model from the physics point of view. So practically on most of the systems you are you end up measuring the system properties for different inputs and then defining that way the system transfer function. So if you want to get further on system control and how to do it in Octave, then you might actually take a look at there are some self-learning material available on internet on the more advanced stuff. However, here I will try to give you enough of information that you can survive your project work, which is which you already have the theory. So we are talking about this kind of system control. Your controller software goes here, and practically this is how you what kind of system you have, and then you probably end up having PID control, but I would guess in this order: proportional controller first, see how that one works, proportional integral controller to see if you can have the better control the speed. On the other hand, then one step after that, you could also try to this proportional integral derivative control, PID controller, as long as you overcome the problem of the noise on the system. How to tune PID controller, no magic in it. That's one place to find good information, reliable information, how to tune the PID controller. Okay, so let's take a quick, not quick, but a better look at the assignment. DSP assignment number 4. The deadline will be next week, Saturday. Is that next week, Saturday? No, it's not. Sorry, it's supposed to be the Saturday next week. Oh, just a second. I will just take a look at the what the date. Okay, so 28th. I will change that immediately since then come through. Since I'm not going to check these exercises today on a Friday afternoon, unless I have a backlog of exercise returns. I will be checking the rest of the second exercise today, but not the third one. So the deadlines for all of these exercises will be on Saturday. That's a practically good exercise. Yes, somebody is. Yeah. Yes, Nikita.
Yes, now you have changed the publishing date. Now
Oh,
the
it was the
publishing date
publishing
is in
date.
1 week.
Sorry. Oh yeah, good idea to publish it today, maybe 8 o'clock. Yeah. Deadline. I was about to change the deadline. Ah, yeah, today. Is that no? Today is yes 20th. Why doesn't? Okay. And the return day is next week. Yeah, this is all messed up now. Next week. Not October. November 28th at, yeah, that's better. Yes. Sorry. I always mess up with the dates. Yeah. So, yeah, published today, but that time is that deadline is next week, Saturday evening. On Sundays, I might actually start looking at the exercises. Okay, so you have 1 week to finish this one. And let's take a look at what I'm asking here. It starts with the same or similar exercise than as last time. Now be very careful with the signs. Okay, that's minus 1 point SSS. That is minus 0 point SSS here. Double clicking that drawing will give you the better view. Okay, but you have done already a few of these exercises. And just be careful, extremely careful with this A and B, the coefficients that you are using those the correct way. So feedback coefficients go to as multipliers or scaling factors for output, and the feed forward, the scaling factors are for input. You can see it already in here. Yeah, A and A's are for output and B's are for input. Like the left hand side has the Y. So, okay, first comes A on the left hand side, then second on the right hand side. Okay. And now, okay, determine rise time, delay time, overshoot settling time for 2% DC gain for that system. So what you will be doing is defining those points. I can show you some hints how to do that. But on the other hand, this is something that you'd probably have done on analog electronics using an oscilloscope. So same thing, you just need to watch that from, for example, from graph. This is engineering, this is not science. Okay, unit step response graph, and from that graph you can then determine those parameters and also the DC gain. Okay, this is optional part. MATLAB has excellent symbolic math calculation. Octave does not. It's based on the Python symbolic package, and okay, it works, but for at least for my point of view, I'm not going to confuse you about that package. It's rather confusing to use. But anyways, if you are into it, then basically you can do it. I will give you extra point, meaning you can get 10 points without the third exercise, but you can get 11 points if you do this by as an exercise, applying the final value theorem, meaning this one here, meaning you would calculate the transfer function and basically calculate the limit when the z reaches 1. Okay, I think you can just calculate z equals 1 after you have done the calculations. What is the transfer function of, well, the transfer of let's see. Okay, that should be actually the transfer function here, I think. Okay, final value theorem, using a final value theorem. Right, so then we have a PID controller, 3 parts, and there are some values again. Okay, haha. The 5 divided by SSS, 10 divided by SSS, and then SSS divided by 1000. Though those are the gains for each of those variables here, initial values, and calculate the corresponding equivalent controller transfer function. So transfer function of that one, and as the single rational polynomial, meaning h of z of that one. Okay, it's not that bad. It's quite nice paper and pen exercise, I would say. You have done more complex systems already on the second exercise. Those are 3 parallel systems instead of 2, which means that you just, well, calculate the sum of those individual transfer functions. Okay, and do the math so that it's a rational polynomial, not just those sums. Fifth one is simple second order system described in question 1. So you would be using this as a plant. That's our system. Okay, and you have the previous controller, and again now you calculate the closed loop transfer function using feedback is simple 1. Okay, and calculate the closed loop transfer function again as a rational polynomial. Rational polynomial means simply that h of z equals b0 z2 minus n plus b1 z2 minus n minus 1 and so on. And here we have a minus n plus da 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 da. Or actually that's rational polynomial. You can also just give what are the parameters b and a. What are the parameters b and a? Either that or system coefficients a and b. Either or, as long as it's defined uniquely. Polynomial. Okay. All right, and then calculate unit step response for the control system, meaning what happens if we shoot the system with the unit step in here. What is the output? Okay, great. And then you would add just a control parameter to obtain better rise time, settling time, and smaller overshoot. How much better? Well, it does not define. If they are worse, then I would be actually quite concerned about, this kind of experiment. If you get even a little bit better, okay, then you know which way to go. However, when you are tweaking one parameter and then going to the next one, the transfer function changes, and yes, it affects also the affects they say basically a cross they are affecting each others. When you are tuning one parameter, then you are losing something from another one. Just like in this one on the PID, this, okay, camera is my camera. Okay, just like in here on the PID, that experimental way, trial and error method. First, you would make it so that it oscillates at a constant rate, but then when you turned a one parameter, which is the first the I, you get higher overshoot. Okay, so when you are changing one parameter, then you lose something, and then the overshoot can be compensated by adding the derivative part there. In principle, you are aiming at what in analog electronic is called the what was that called? Let's see. That's the set value. Something like this. Step response. So it's not overshooting or undershooting, but goes optimally in between. Now, of course, it doesn't. It should go like that. So that's the optimal, but hard to achieve. All right, so next one include an external disturbance source. Okay, you would be using now the this model where your input is considered to be the disturbance. The reference value is now whatever it's actually zero. You can assume the reference zero, which means that you have the disturbance as your input, and then you have directly the planned and controlled output. You have the feedback loop and controller in cascade as an error signal to this input. Oh, yeah, no, the feedback signal for that input, yes. So in that sense, our new error signal for disturbance is right here. And basically external disturbance source, and then, okay, what is the transfer function? You need to figure out that one first. And when you know the transfer function, meaning the system coefficients, then you can calculate the or determine the rise time, delay time, overshoot, and settling time the same way you did already. And that's all 8 questions, giving you maximum points of 10, since this is considered the most important exercise for you on this DSP set. Okay, so what to do, what to do, what to do. Wait a minute, where's my... There. On Octave. There we go. So let me first start from a system that I have done. Let's see, I think last week, did I do something? Did I make a system last week? Spectrogram. Okay, I have done some systems last week. Design from zero pole plot. What is that system? This is a second order system. Maybe I can actually just run that part. Not... Hmm. I don't want to run the whole thing though. Okay, I'll just copy that one to new file. Okay, there we go. Unnamed, not a good name. Save as, not history 3, exercise 3, but exercise 4, not history, but the system. Scale it, group delays and such. There we go. So I have this kind of low pass filter as a second order system. So based on the location of these poles, I would guess that this has some, this actually has some overshoot. Let's see how much it does have. So we calculate the step response. The old-fashioned way. I start from -10, go to, for example, 100. So this is our region of interest in samples. We could have a sampling rate there also, but well, it does not really make much difference. Just remember that if you have a sampling rate, of course, then you, if you know the sampling rate, then you can tie everything into the real time base. So maybe I will just use something here. Sample rate. And at the same time, I could actually calculate the sample time. And then I can actually do the time vector, which is simply nn times ts sample time vector. So those are the points where the samples are made, and then I have the unit step equals double nn greater than that equal to 0. So I have a unit step function. In this graph, yep, looks like unit step. And then we can calculate the step response. SS equals filter B A N, not N. Well, it would be the same, but anyways. not the same. Okay, there. This is the step response, unit step response. BB and AA, actually, I had them calculated here. So maybe I should actually they were calculated here on the file. Yep, yeah, I can show you those. Those are the values. And it doesn't actually matter if you use the just numeric values or calculate them from there. So, alrighty then. Then the step response was calculated when I can actually put the figure in here and this step response. Hey, that's nice. I actually got some overshoot and stuff there. Okay, so that's my system. And now let me put a couple of lines there to make the delay time. Delay equals time from 0 to 10%. So I can draw here a line. Let's see. Delay line equals line. Okay, line. Actually, I think I need some help line. X data, Y data. Yes. Okay, so DL, no, yeah, delay line equals to line. X data is minimum of n to maximum of n, and Y data is simply 0.1 and 0.1. That should actually draw me a line at 10%. Oh, that's nice. Okay, there are some properties on that line actually. If I draw set DL, I can see what kind of variables I can change here. I can, for example, change the color value, but anyways, so let's skip that part. But anyways, this line actually gives handle also to the object, so you can then change the line properties afterwards. Okay, but anyways, the let's continue. That was the 10%, and now I can find, okay, with some zooming, it looks like the so we have the delay time equals 2 time steps equals, which is 2 milliseconds. Okay. Another line, then the rise time RL equals, let's take the DL first. Change that to RL, and that's the 90% rise. Whoa. That happens when your fingers are faster than. Okay, but nothing to worry about. I just clear my RL and oh, it didn't do it. Okay, whatever. But anyways, that's my rise time. But rise time is practically time from 10% to 90%. So we have 15 time steps, which means 50 milliseconds. So we have the rise time from 10% to 90% is 50 minus 2 time steps, which is 13 milliseconds. Okay. Now I have rise time, delay time. Next parameter, what I want to know, overshoot. Overshoot is simply the value of highest point here, which can be actually also calculated overshoot. Overshoot is the maximum of the output compared to level where it's setting. Now we have gain of 1. Okay, maybe I'll just estimate it from here. So this one is settling actually at 1, but on the system which has higher gain, of course, this settles somewhere else. And there, I'll just put the line. Well, I don't need the line. I don't need the line, but I can actually just guesstimate it from here, maybe. Well, that's the highest point. Also, we have overshoot of 0.061. So overshoot is the difference. So it's 6.1% overshoot, which is not much. And then basically, how about settling time? And make it something like 2% settling time. So for that one, we need to calculate the plus minus 2% of the maximum gain. So again, if a system have DC gain, this is relative to that one. So settling time, I would make this RL, and the lower line would be not 0.98, 0.98, and that one is 1.02, 1.02. Ha! Sailing time from the definition, actually, that's the last point after the after it basically starts remaining here. So the sailing time in this case is 35 time steps. 35 time steps. equals, in this case, 35 milliseconds. Ha! No magic, as you can see. I just have that extra green line. Don't worry. Don't be too confused about that one. It's just an artifact on my graph since I pressed the enter too fast. Okay, final value theorem, screw that. So fundamentally, what we are looking at, the DC gain here. DC gain. Do we have a unity gain here? Whoops. Does it settle to 1? It does not. Yeah, DC gain. So everything is actually, it's not that, I didn't get exact answers now. I started looking at, hey, wait a minute. That's plus minus 2%, and that does not look quite okay. So DC gain for the system is simply let's see. It is the frequency response at 0. BBAA at 0. This should be DC gain. Oh, sorry, 1024. Okay. The first value of that one would be the, okay, something like that. So DC gain can be calculated so that we calculate the frequency response first. First value is the DC gain. That is the DC. DC gain. Yeah. Let me take another figure now. I should have first calculated the DC gain, but on the other, it's about 1. Okay, maybe I'll just do it this way. Calculate first the DC gain. Do the things the right way. Let me now go over again what to do. So this is more or less now the old picture. Let's close that one. So figure, new figure. It has the unit step response. We calculate the DC gain. Then we can have lines like DL, that times DC gain. That's our 10%. It does not change, of course, the value here. Then we have the rise time was defined from this curve, again related to DC gain. Then basically the overshoot, the percentage can be calculated somehow, but anyways, that's then the lower this lower 2% line. The higher 2% line. Okay, and now we have those lines correctly here, and we can see, okay, it did not change this value. It's still 2 time steps. Maybe a little less, but anyways, in reality, it's 2 time steps since you cannot take the fractional time steps in digital systems. Rise time, it didn't change that. Also, you have 2 time steps, and this is 15, so we still have the 13 time steps in between. The maximum now, actually, it's not 6 point some percent, but it's basically, let's do the overshoot again. So we calculate the maximum of step response minus DC gain divided by DC gain times 100. So this is in percents. Okay, we have 6.72 percent overshoot instead of 6.1. Ooh, big difference. Okay, and I think we still have about the same. Okay, now it's 36. Wow, it changed the settling time 36 milliseconds. Okay, something like that. And now I've gone only 2 of the first ones. But anyways, the following is quite straightforward. PID control combines 3 parallel blocks. So if you have parallel blocks, just for fun, I will do a parallel blocks of 3 systems. So this was low pass filter. So it could be used as an integrator, right? Integrator actually is our example system, which is a low pass filter. Ideally, you would use, and in this exercise, you would use exactly that transfer function. Integrator's transfer function is z divided by z minus 1, and then you have this the scaling factor of k there. Integrator, and then we have the scaling ki equals, okay, 5 divided by 1, so I'm 0.0, I will just put 0.05, let's see what happens. Then basically we have the just a unit system which has the proportional part, kp equals, okay, then 0.1, and then we have the derivative, which is basically a it's a well, there's the transfer function. So if I mark here BB derivative is actually 1 minus 1, and AA derivative part is the just 1 and 0, just for fun. This is first order derivation. Doesn't do much if I just put it there. So this is our system. And now we just calculate the transfer function for, I'll calculate the transfer function for the PI. Which is simply HI plus HP equals pen and paper, not red, blue. This is simply a factor KP, transfer function of KP, and then we have the transfer function of KI times that system BA what we have, parallel. Okay. H of Z for PI equals KP, that's just a multiplier, plus, then we have that polynomial B Z to K minus K A times Z2 minus K, meaning that you need to actually do something like that. Sigma A Z2 minus K plus B times Z2 minus K, okay, sorry, KP times that. And that one has the KI times that. KI divided by the common numerator, right? Ha! Oh, that ain't bad. So we have the A's and B's known, and we just have the KP and KI there. So practically the transfer function is the BB of PI controller is simply KP. Okay, I see. KI equals 0.05. I have those just comments. Equals 0.1. And we have the BB PI equals to KI, KP times BB. No, AA, sorry, yeah, see. This is how easy it is to make mistakes here. Plus ki times bb. Or maybe I should actually just, so I have the kp times aa plus ki times bb, then it's exactly how it is there. It's just multiplied the coefficients. These coefficients are multiplied with that one and then added together. So those are vectors actually added together. As long as your a and b have the same order number, meaning with the tailing zeros so that the vector sizes match, then adding systems together is very simple. Okay, there, that's the PI controller, my PI controller, the numerator coefficients. And AAPI is simply the same as AA. PI controller denominator coefficients. And now we have a system. And now we can do, basically with that system, we can do, for example, zero ball plot, Z-plane, BB, PI, AAPI. That went somewhere. Not that one. Was it that one? No. Sorry. Let me put it on different window. I think I just destroyed a picture. Okay, looks like that. Looks like we have a stable system, which is very good for a controller, that it's a stable system. We have 2 zeros, 2 poles. It does something for the system. So actually, yeah, that can be used as a part of a control loop. Next, you would calculate the transfer function of the simple closed loop transfer function, meaning the input is here, you have your own transfer function at the middle, then you have a system here. I think I used my the example as my low pass filter was used. Well, okay. Yeah, you would use your Q1 as a plant here. I used my Q1 as the low pass filter or integrator. Okay, just follow the exercise questions. Don't follow too much what I did here. All right, so then you just calculate the transfer function for that. And what is a closed loop transfer function? That's straightforward to calculate. If you did it already on, say, second exercise, that was quite close to that. If not, you have now a little bit more material for it. That's something you need to know how to do. You are an electrical engineer, damn it. Behave like one. You need to be able to calculate transfer functions, period. All right, and then again, DC gain doesn't necessarily be 1, by the way. At one point it was 1, but anyways, calculate the DC gain, rise time, delay time, overshoot, settling time. Then adjusting the control parameters to obtain better. And okay, meaning that you will just fiddle with those. Change a bit, see what happens. Either to the rise time, settle time, or overshoot. And basically, more you put gain, faster it comes, at some point it gets critically stable, meaning that it starts oscillating. Okay. Then actually with this integral part, you can control the oscillation, so you get the damping oscillation with higher overshoot. And with derivative part, you can then start going lower with this overshoot. More gain on the derivative should give you better overshoot. Okay, good. So, and the last one, you need to calculate the transfer function again, but not for the control system, but for the control loop. So the classic control loop feedback, that's a controller plant signal feedback. So for the disturbance part, you will see this is 0, meaning that you have a system which looks like this. You have the disturbance coming into this error part. In here you have the control as in a feedback loop, and yes, you have the plant here, and that's the output. So you would calculate the H of Z for this system, and then you can take a look how much an external effect actually disturbs this system. What is the rise time? What is delay time? What is the overshoot? How fast it settles? So that tells you how well your control loop is actually taking and reducing the effect of external effects, like, well, on heating system you have external heat source in addition to your heater, for example that sun, or on the this cruise control you have uphill or downhill, or in any engine you have a variable load. That will be your external effect. And as you can see, you can then start playing with, can you find, for example, cases that this comes if you have an input, oscillating input, do you get into an resonance of the system so that it starts resonating and practically breaking. So all sorts of things you can start analyzing using that transfer function. Okay, that was my part, and your part is to go through the exercises with some extra care, and find out if you can actually this should help you understanding how PID controller actually works. So the first part is just simply finding the transfer function of a system. You would be using this transfer function as your plant, and you characterize the plant with the unit step response. Calculate the unit step response, which determines the DC gain, rise time, delay time, overshoot, and settling time. Okay, and after that, you make your PID controller using your own SSL values as initial values. Um, and by the way, this should end up being a stable system. I'm say fairly nicely behaving system for all SSS numbers. I have tested that one last year. Okay, and then you have the controller's transfer function. Again, when we are asking you to draw the transfer function, it's also or system coefficients A and B. It's the same thing in MATLAB Octave environment. Okay. It's exactly the same thing. The coefficients A and B or B and A, whatever. As long as you use those the right way. System coefficients A and B, what are those? That defines the transfer function. If you want to, there are some tools actually to have a nice plot of the transfer function. At least in MATLAB, you can actually have a really nice LaTeX script to produce the real formula for transfer function. It looks nicer. Okay. And the plant was a simple second order system here, and then transfer function. Hey, wait a minute, what happened here? What did I break? Huh. I broke something. Okay, yeah. I broke that picture. Okay, so yeah, that's all for now. So if you have any questions, please ask now. There's still some time for explanations.
I have a comment.
Okay.
When you're programming, it's quite difficult to follow it because your pace is quite fast.
Yeah.
If I'm trying to also program this at the same time.
Yeah, that's a fair comment. I do that a lot. I'm very sorry about it. On the other hand, I will again put the history file first to the space, and then I will produce those videos that you can go that through that material on your own time on your own space.
Okay.
Yeah,
And
I try to be, not to get so enthusiastic next time. So maybe I have had too much coffee today. Sorry about that.
also the template, it's not accessible right now.
Wait a minute. Why is that? Ah, what? Okay. Anyone in this in Metropoli Ammattikorkeakoulu? So okay, but anyone actually this is just fine. Anyone with the link. So you may have been accessing with your personal the Google account.
Yeah, now it works. Thanks.
Okay, yeah, no worries. Anything else? Okay, if not, I will be stopping the